To the uninitiated, the ability to guide a boat across an expanse of trackless water seems almost magical. Reduced to basics, though, navigation is just the process of answering two fairly straightforward questions. Where am I? And where am I going? On land, we take the process for granted. The sea is a less familiar environment than the land, and there are no roads or signposts to follow. The aim of this video is to explain the principles of coastal navigation so that you can escape from the familiar playground of your home waters and make more extended passages along the coast by day. And with practice and experience, the same technique can be used at night or for brief forays out of sight of land. Without signposts and without being able to stop and ask the way, maps, or charts as they're called at sea, are the most important of the navigator's tools. Charts are produced by various commercial publishers, or, like this one, by the Admiralty. It's a very accurate, detailed map of our cruising area, showing the land, coloured yellow, the sea, coloured blue in shallow areas, and white, where it is never less than 5 meters deep, and those areas which are sometimes land, sometimes sea, coloured green. The depth of water in meters is shown by numbers, called soundings, and by contour lines, while symbols indicate hazards, navigation marks, and useful landmarks ashore. Some symbols are self-explanatory. It's easy to see, for instance, that this is a buoy or that this is a rock. Others are less obvious, but all are shown in the so-called Chart 5011. It's not worth trying to remember them all, but you'll quickly become familiar with the commonest ones, and you can keep Chart 5011 on hand to explain the odd ones. Out on the water, we're leaving Plymouth, heading towards this point, a mile west of the Eddystone. The end of the breakwater is close to starboard, so we must be about here. It's easy enough to draw lines on the chart, but we can't draw lines on the sea, so some other means is required to relate the boat's passage through the water to the line on the chart. The compass shows the direction which the boat is heading, while compass roses show the corresponding direction on the chart. North is marked 0 or 360, and other directions are given in degrees, measuring clockwise from north. So, east is 090, south is 180, southwest is 225, and so on. Directions are always given as 3 figures, with the noughts pronounced as 0. Most boats use a magnetic compass, whose working part is a magnetized needle hidden beneath the card. This keeps itself lined up with the Earth's magnetic field. Unfortunately, the Earth's magnetic field does not run exactly north-south, so north on the compass doesn't quite indicate true north, but points to the so-called magnetic North Pole. The difference between true and magnetic north varies from place to place around the world and from year to year, so it's known as variation. The boat has its own magnetic field as well, and this tends to deviate the compass from magnetic north, an effect called deviation. A skilled compass adjuster can fit weak needle-like magnets to the base of the compass to reduce the amount of deviation, and will then produce a card showing the remaining deviation on different courses. Knowing the direction and extent of both deviation and variation, it's a matter of simple arithmetic to convert the direction shown by the compass to true. The mnemonic, "True virgins make dull companions," serves as a reminder of the relationship between true, magnetic, and compass. While the cadet rule is a guide to the arithmetic. The word cadet shows that to get from compass to true, easterly corrections should be added. Suppose we're steering 195 degrees by compass. The deviation is 2 degrees east, so the corresponding magnetic course is 195 plus 2 equals 197 degrees. To convert from magnetic to true, we would add easterly variation, but here the variation is 7 degrees westerly, so it must be subtracted. The true course is then 190 degrees. Many navigators skip the last stage and work in magnetic all the time, using the inner ring of the compass rose. It doesn't matter very much whether you work in magnetic or true, so long as you choose one and stick to it. We still need to find the direction of that line on our chart. It would be remarkably convenient if it happened to pass through the middle of a compass rose, but of course it doesn't. The traditional tool for the job of transferring directions from the course drawn on the chart to a compass rose is a set of parallel rulers. First, the edge of one of the rulers is placed along the pencil line. Then, keeping that ruler pressed firmly against the chart, the other ruler is moved away from it towards the compass rose. When the rulers are fully open, the second ruler is held firm and the first moved up to it. With a little practice, it's possible to walk the rulers quickly and accurately around the chart in order to read the course directly from the compass rose. The track from the harbour entrance to the Eddystone is 214 true or 222 magnetic. Because we're navigating a boat, not a night school desk, it's more realistic to ask the helmsman to steer 220, but let's face it, on a small boat we would be kidding ourselves to pretend that he could really steer accurate to 1 degree. Some people, particularly those working on very small chart tables, prefer to use a proprietary instrument such as this Breton plotter. The end of the instrument is lined up with the pencil line, and the movable compass rose in the centre of the instrument adjusted so that it's in line with the grid lines marked on the chart. The direction of the pencil line can then be read off directly in true or, using the variation scale incorporated in the instrument, in magnetic. In a car, we can keep an eye on the mileometer to judge the distance we've travelled. Afloat, the corresponding instrument is the log. Several types are available, operating by measuring the pressure created by water moving past the boat's hull, by electronically measuring the speed of rotation of a tiny impeller mounted below the hull, or, simplest of all, by mechanically measuring the number of revolutions of a spinner towed astern. Distances at sea are almost invariably measured in nautical miles, and speeds in knots, a knot being 1 nautical mile an hour. A nautical mile is about 6,080 feet, or 1.15 statute miles. To see why this unique unit should be so universally accepted, we need to look at the Earth as a whole, rather than just at the small area shown on the chart. The position of any point on its surface can be defined by reference to a grid of imaginary lines. The vertical lines running from pole to pole are called meridians, while the horizontal rings are called parallels. Looking down the globe from a point immediately above its north pole, the meridians appear as straight lines radiating from the pole. One meridian, called the prime, or Greenwich meridian, passes through Greenwich just east of London. The others are named according to the angle they make with the Greenwich meridian. Looking at the globe broadside on, the parallels appear as just that, a series of parallel lines running across the surface. The longest, midway between the poles, is called the equator and is designated 0 degrees. The other parallels are named by the angle between them and the equator, measured at the centre of the Earth. Latitude, north or south, and longitude, east or west, together give the worldwide grid position of any point, and a part of the grid appears as horizontal and vertical lines on every navigational chart. Each degree, whether of latitude or longitude, is subdivided into 60 minutes, and for real precision, each minute can be further subdivided either into 60 seconds or, more often, into tenths and hundredths. The exact position of the Eddystone Lighthouse, for instance, is given as 50 degrees, 10.8 north, 4 degrees, 15.9 west. A nautical mile is defined as 1 minute of latitude, so the latitude scale on the side of the chart is also the scale of distance. The longitude scale across the top and bottom of the chart is useless for this purpose, because although a minute of longitude is almost exactly 1 nautical mile at the equator, it decreases to nothing at the poles. These single-handed dividers, so called because they can be opened or closed with one hand, are used to transfer distances to and from the latitude scale. On the passage from Plymouth to the Eddystone, the distance is 10.9 miles. Even on a passage as short as this, there are other factors to consider. Sailors are usually well aware of the wind, but it can have an important effect on powered craft as well, making them drift sideways. This is known as leeway. The extent of leeway is difficult to predict with any accuracy because it depends on the strength and direction of the wind, the speed of the boat, her hull shape, rig and superstructure, and even the sea state. For a sailing boat, it's the greatest when sailing close-hauled and reduces as the sheets are eased onto a reach, becoming negligible when running downwind. For a motorboat, it's negligible when the wind is dead ahead or directly astern, and greatest when the wind is abeam. As leeway can be as much as 15 degrees or so, it should be allowed for. You may find it useful to draw an arrow on the chart to represent the wind direction and remind you to steer upwind, or you could try the mnemonic "take port" to remind you that you should take away the angle of leeway if the wind is on the port side before telling the helmsman the course to steer. Having just cleared the breakwater, we intend to travel along this line, 220 magnetic, but the wind is blowing from the starboard side and we estimate 5 degrees leeway. Although the course is plotted on the chart as 220 degrees, our helmsman should steer 225 degrees. Details of the time, course, log reading, and anything else of navigational interest are noted in the deck log. It will never be a bestseller, but there's enough to check back on the chart work if things go wrong later in the passage, and perhaps to assess the boat's performance. Now, an hour later, the log reads 114.6. So a look at the deck log shows that the boat has travelled 6.4 miles from the breakwater. Knowing the course steered and the allowance for leeway, the skipper can plot a position on the chart. On a course of 220 magnetic, 6.4 miles, he marks the position with a cross and the time. The cross is the standard chart work symbol for a dead reckoning position, or DR. Strictly speaking, a DR should be based only on the course steered and the distance travelled, without allowing for leeway. But, as it will have to be accounted for somewhere, most small boat navigators do include it in their DR. According to the DR, the lighthouse should be on our port bow, but it's not. We're heading straight at it. The reason for this discrepancy is simple. The DR is based only on the boat's movement through the water and takes no account of the fact that the water itself is moving. Tidal streams of 2 or 3 knots occur frequently around our coasts, and in estuaries and harbours can often be seen rushing past buoys and moored boats. At sea, they run roughly parallel to the shore, so their effect is immediately noticeable when making coastal passages. A typical sailing cruiser is unlikely to average much more than 6 knots, so if she's fighting a 3-knot tidal stream, it's like running up a down escalator. In 1 hour, she moves 6 miles through a body of water which has itself moved 3 miles in the opposite direction, so her speed past the land is only 3 knots. If, on the other hand, her skipper has managed to arrange things so that the tide is in her favour, her 6 knots through the water will be augmented by the tidal stream, and she'll be rushing past the coast at 9 knots. As the name suggests, tidal streams are related to the rise and fall of the tides, so this is a good moment to take a break from chart work to look at tides in detail. Tide tables are published by the Admiralty and in commercial almanacs. The data may be presented in slightly different ways and in more or less detail. but whichever book you use, the principle is similar. Each section of the tables gives the time and height of high and low water for every day of the year at a particular major port. At Plymouth Devonport, for instance, on the 2nd of May, the tide tables show that high water is at 0600 and that the height of the tide will be 5.2 metres. Low water follows at 1204, when the height of tide will be 0.9 metres. These times, by the way, are in GMT. It says so at the top of the page. So, during the summer, an hour must be added to the times shown to convert them to British Summer Time, BST. It's worth noticing that, though there are variations, it takes just over 6 hours for the tide to rise from low water to high, and about the same time for it to fall again. Superimposed on this twice-daily routine is a fortnightly pattern. On the 2nd of May, the range, the difference in height between high and low water at Plymouth, is 4.3 metres. A few days later, high water is lower and low water is higher, so the range has decreased to 3.9 metres. It continues to decrease until the 9th of May, when it reaches a minimum of 2.3 metres, before increasing again over the next week. Tides with a large range are called springs, and those with a small range are called neaps. Earlier in this video, we mentioned that the chart shows the depth of water by soundings and contours. Sea level, however, is constantly rising and falling, so the charted depths have to be related to a standard level, roughly corresponding to the lowest of low tides, known as chart datum. The heights given in the tide tables relate to the same datum level, so at high water on the 2nd of May, a channel shown on the chart as being 1.5 metres deep will actually have 1.5 plus 5.2 or 7.7 metres of water.